Today we're going to talk a little bit about the consequences of AI. We're going to talk a little bit about a different aspect of of thinking about your infrastructure and applications, especially around power monitoring. So, power consumption. I think the theme of today is less about it's about how the application that we build impact the future of how you run them. And we're looking at power consumption both from an operational and sustainability challenge. Yes, we want to be green, but as you will see later, thinking about power consumption has a material impact about how firms will be running in the future. But also we're thinking about what does it mean to measure this, And we're going to look at the in a more granular way. But more concretely, we're going to introduce Kepler as an open source project that actually kind of enables you to monitor applications at a more granular level and what you can do with it. So I'm going to hand it over to Aric here.
Thanks, Marius. So I think what's important is the old adage, you can't manage what you can't measure. So it's always been kind of a black box in terms of what power you're consuming. Going back years when we designed data centers, we knew how much power we can get per rack. We started figuring out how dense we can make the rack. And we were never fully populating those racks because we just didn't have enough power. And what we see now is that, notwithstanding, with AI, there's a huge demand. The chips they have today, generally speaking, are huge consumers of power. Okay? We have clients, banking customers, who are making decisions today based on power. Okay? They're maxed out on a data center. They're going to a different data center because they just can't get enough power to fuel what they want. As AI becomes more and more pronounced, those chips are going to come in. They're going to more densely populate those racks. People need to be thinking about how do I consume power for my applications. So here's some numbers from Barclays just talking about the impact of AI. They're talking about upwards of 9% of data centers consuming electricity in this country. Okay? It's a staggering number, 3x what it is today. And if we go forward, we've got Goldman talking about 160% increase in data center demands. We have articles talking about how the power utilities are not pulling power to data centers, more power that is, because of a constraint. They can't produce the power. So we're getting to a point where it's a constrained resource, and you're going to need to make decisions based on that constrained resource, like any other constrained resource. Bandwidth is a constrained resource. Budgets are always a constrained resource. Power is another one as well. So the thesis here is that what we need to be able to doing is using technology such as, say, Kepler, to understand where are we drawing power, and then we make decisions that best allow us to move forward. So we care for really three key reasons. One is operational risk. If I'm looking to build out new capacity in my system, if I'm looking to handle surges due to triple witching or what have you, if I'm looking to handle a new product and we're going to 2x or 3x or 10x of my volume, I want to know what power I'm consuming and do I have enough power to meet those growth demands, those spikes. So there's an operational element to this. There's also a sustainability aspect to this. We all live in the world. We want it to be a greener world, not, Pittsburgh in the 70s with smog and so on and so forth. Okay? How can we be thoughtful about what our output is and where we run these things? Again, if we can measure it, we can improve it. And last is the FinOps aspect to it. If we can be consuming and running systems that are more efficient, not only does it make it greener, but quite honestly, it makes the CFO happy. He or she will be happy that we're spending less money. So if we can think about performance per watt or watts per dollar of P&L or anything like that, we can start having different calculations and different conversation about what we're doing. But the premise here is that we have to understand what's happening with the power, which applications are using power, and how do we improve upon that.
And I think this is important to kind of think of what's the angle that we're coming from. So so far we kind of talked about what we want to talk about today. It's probably kind of it's a good moment to actually also introduce ourselves, which I think we kind of skipped in the beginning because we're so quick to rush in the matter. Yeah, you've seen our names, but Aric here is working in our global financial services team. And Aric, maybe you can say a couple of words about that and how you see sustainability kind of being part of the
Sure.
company.
So I serve as the chief technologist in Red Hat's global financial services practice. In that role, I support the enterprise financial service clients around the world, all the names you're familiar with. Prior to here, I spent about 20 years in the banking space at a tier 1 bank, CTO, co-founder of some equity and FX trading shops. And during a lot of the time, running, managing, building, designing, trading systems. So power and is an aspect of what I have to do in my life.
All power intensive things. Yeah. And my name is Marius Bogoevici. I work in the field CTO organization, which is the engineering part of Red Hat that's focused on working closely with the field and, driving the technology strategy of Red Hat based on the interaction with our customers. So, I'm coming from a financial services background, and Aric and I have worked a lot with our clients. And we've seen, I think, an uptick.
Can I add one thing also I should have mentioned? I'm a board member of Finos as well. So if you have any feedback on Finos and OSFF, please let me know. Good or bad, they want to improve the organization.
You left the most important thing at the end. So that's so yeah. I think the and this Kepler, the project that we're talking about, is a Finos is a CNCF project. So they're all kind of part of the kind of larger Linux Foundation family of open source solutions that are trying to create in the end and enable an open framework. Because what we see kind of coming back to the discussion of okay, what's important? What do you want eventually? Do you want to drive the cost down? Do you want to be green? Do you want to kind of put those things on on your balance sheet in one way or another? No matter which way you do it, it has to be data-driven in a certain way. And frankly, some of the some of the backlash, in this kind of whole conversation about where you are is, the lack of actual data. There's a lot of estimation, there's a lot of assumption, and I think what we see is a lot of coarse granularity. I know, for example, how much a data center consumes. I know a little bit less about how we got there with those numbers. So when we see this kind of when we see this sustainability framework as being data-driven, it's obviously a combination of being able to observe the power, to observe information, how much carbon, what's your carbon footprint, what is your power consumption. Obviously, you want to gather that data, analyze and report it, and that. Where does that put you? You have a report, what do you do with it? That's fine, you have information. So you kind of end up, taking various decisions that allow you to optimize your platforms and workloads.
Can I just add one thing also? The premise that I have is that, many of the banks have carbon goals. Net zero by 2030, 2050, whatever the number is, okay? So we're going to get to the point where the CIO or the chief sustainability officer is going to dev teams with a report that says, hey, here's our 1,000 applications that we run here at the bank. Here is the usage of all those in terms of watts or carbon footprint or whatever it is. And I need each of you to come back and tell me, reduce it by 10% by this date. Reduce it by 15% by this date. And by using tools such as Kepler, allow us to get to that point. Know A, today, what we're using, and then B, understand those usage patterns, the whens, are there peaks, are there valleys, and then think about that as Marius talks you through Kepler.
Yeah. And I think, I think what you're saying, Aric, is very, very important, because you kind of said the thing in the beginning, which is, only what gets measured gets improved. And the whole this whole virtuous cycle that we're talking about actually starts from getting some data, at a certain level of accuracy. And this is basically kind of our primary focus for today. We're obviously kind of the data that you're getting in here that you will see collected with Kepler can go into reports, can drive decisions, but we're going to focus on how you get how you get data, actual data about your applications, about your kind of like your workloads, concretely, and from this, from your environment.
And that happens whether it's on-prem, in the cloud, bare metal, virtualized.
Yeah,
Okay.
it's essentially kind of like, well, we'll talk about, different solutions have actually different, like Kepler is kind of an evolving framework. And, we're going to talk immediately about what Kepler is and what it does. But the idea is that I want to have this consistency across that Aric is talking about different environments, about different levels of granularity, and, kind of understand and make decisions based on that. So, what are the key components or the key pieces of Kepler as a framework? As I said, Kepler is a CNCF sandbox project since May 2003. It's a young project, it's an evolving project, it's an open project. So you will see, certain architectures being supported. You will see, a call to action to contribute and add new architectures. But the idea is to provide a comprehensive and, kind of like a comprehensive way to gather data at, the process, container, or pod level. About different aspects of the power consumption of a specific workload, like CPU, GPU, RAM, anything that's happening on the board, supporting different types of architecture in there. It's built with, and we're going to talk a little bit of the details later, but it's built with the idea of being making a very little impact on the measurements. A tool that kind of like increases your consumption, for example, is not, when you're trying to reduce it, is not a very good one. So we're trying to be as, economic as possible in that. And, because a lot of it because it for certain environments, it uses a mix of like estimation and actual measurement. So for example, there are environments in which you cannot measure the power directly. There's a big investment in machine learning. I'm applying machine learning into, in producing this data. And there's an entire science behind it. Like there's an, entire corpus of papers that actually kind of describe how to attribute that consumption based on these models. I'm not going to dwell into it, but I'm going to talk a little bit about how it comes into play as part of the architecture.
You want to show them it?
I think so.
Okay.
I think
enough
we
of the
should do
slides.
that. I think we should do that. I mean, I already did, because I think you saw the dashboard already.
So what do we see here?
So, in fact, this is a default dashboard that is created for OpenShift using Kepler data that's collected in Prometheus. It's a Grafana dashboard. So it's just one of the flavors in which you can consume the Prometheus data. What it's showing you here in particular, it's basically showing, some information about the architecture. So it's kind of telling you where the data is coming from and how. And I should probably increase the volume a little, the resolution a little bit. So it's giving you kind of the types of processors and what's the source. It's an estimated measurement because we're running everything in Amazon, so we don't see exactly the power consumption, but we kind of tell what's going on in there. I can see the total energy consumption in the last 24 hours for the whole cluster. It's not the granularity level that I was talking in the beginning, but it helps me understand where is the kind of like how much this cluster has consumed.
But since it's based on Prometheus and Grafana, you can go back and say, what was my power consumption this quarter versus last quarter?
Exactly, and you can aggregate, like you can build this as a different levels of granularity. Again, we put it by default 24 hours, you can go back, you can change it, you can collect data differently, but you can see it and visualize it. And we can see that it always grows because there's always more energy being consumed. I think one interesting thing that kind of ties into the discussion we had before about optimizing comes with, showing the energy consumption in different namespaces and different projects. So if I have a project, if my business unit has a project and runs a certain set of applications, and Aric's business unit...
Let's back up a second. So namespace for those people that maybe are not as familiar with Kubernetes.
How many of you are familiar with namespaces in Kubernetes?
Some. Okay, so let me back up a second.
So let's back it up for a second. Very good point. All right. So namespaces are, when you think about like multi-tenant architectures, like when you think about running, a bunch of applications in different clusters, namespaces are a way to organize that in, and slice and dice basically the cluster capacity and isolate, for example, my applications from Aric's applications from your applications. Each one of us kind of gets to deploy their applications in a portion of an OpenShift cluster.
And that namespace is definable. So it could be super granular, like every application is a separate namespace, or the namespace could be payments, fixed income trading, equity trading, whatever the firm wants to define when they host these applications inside of Kubernetes, they have that namespace, and then we're reporting based on that at that level of granularity. So I know at a bank, for example, we refer to them as DIDs, deployment IDs. So that could be the mapping here for your namespace. Therefore, you know that my set of applications is using X watts and yours is using kilowatts. Mine's more efficient than yours.
In this example here, you actually see a bunch of them, right? Like you see, the majority of them are actually system. It's a very small cluster. It's not very used. We only have a very small demo running on it. So you can see, that most of the energy consumption for this particular example that we're showing right now is going into the system. But you can also see that, this sustainability demo namespace in which I have two applications, one newer, one legacy, is basically, consuming, 741 watts hour. It may not be a lot, but imagine that it's just something that I started this morning, and it's already kind of consumed like a light bulb running for a number of hours. Most importantly, what it's showing me also, it's showing me, and let me refresh this for a moment to get some newer data. It's showing me, some measurements over time. So I can see, for example, that at certain points in time, this namespace has started consuming more or less. The applications go under load, more or less. I have two pods.
Scroll up for a second, but you also can see the components inside the machine. So you've got the CPU, DRAM,
yep.
GPU. So you can see specifically what is happening. So if you're running an application and you're like, well, what's consuming that? Am I CPU bound? Am I GPU bound in terms of costs or in terms of green? You can see all that.
Let me try to generate a bit of load. I have two running applications. I'm getting to a part that I wanted to show you. And I think, Aric, you kind of anticipated that a little bit, where I can see, and it'll probably take a little bit of time. This is not designed to, be kind of a real-time dashboard. It's more like a data collection tool. So it'll take a little bit of time to aggregate this data and kind of bring it back into the dashboard. But you can see that I have, for example, two versions of the same application running in, side by side. And I can already tell that under the same load, one of them is consuming, more than the other. It's consuming a lot more than the other. And, if you have a little bit of time at the end, we can show how this looks after running a little bit of, after running this for, for some more time. But the point is that I can now have a tool that basically allows me to make decisions on, hey, I should run this version versus the other version because it is it consumes less power, it's more efficient from that point of view.
So you can do A/B testing.
I can do A/B testing with two versions, and this is exactly what I'm doing right now in a very crude way by basically showing these two things running side by side.
But it's not just in this case. It's your legacy versus using, say, Quarkus.
Yeah.
It could be using this GPU versus a newer one that's claimed to be more efficient. It could be a different model from a different vendor that has better performance per watt.
So
it could be using Intel CPUs with AMX extensions, the math extensions. Yeah. So you could be making a bunch of different choices, but this is allowing you to measure those changes from a performance per watt perspective. In addition, obviously you'd measure for latency and for accuracy and stuff like that.
And again, to your point earlier, I have this information kind of sliced and diced by different pieces, like by CPU, by DRAM, by other parts. So now that you saw that into action, let me talk a little bit about how this is built. Let me go back.
Because you touched upon that the architecture is a bit different if it's bare metal versus virtualized.
I'm going to talk a little bit about
Okay.
that in a moment. Now, this is basically a little bit of the rendering of what you saw from an architectural perspective. Like, these are the namespaces, that we were kind of talking about earlier, and Aric pointed to, that collect, different, the data about different pods. So my applications versus Aric's applications versus your applications, and I can basically kind of like figure out like who of us like has a certain budget and can consume certain things. There's obviously there is a collector built into the into the kernel that kind of like generates that kind of collects that data and produces it to a metrics export. There are two pieces here that are very, very important. One is essentially, the exporter piece, which aggregates the data that you've seen in Grafana and basically creates like the different Prometheus, data points and time series with power data, like at the kind of like application and, at the kind of architectural component level. The other one is the model server that uses an estimation model for environments where I cannot collect the data directly. How are they put together? There's essentially kind of three big pieces in here. And again, this is a very complicated diagram, so I just want to give you a kind of a quick overview. There is obviously the kind of the portion that that's nested in the kernel with the BPF that measures performance. It measures the performance directly. Like in the bare metal use case, which is the simplest one, all I have to do is essentially measure what the application does, from a kind of like CPU utilization, instructions, cache miss, like everything that it does, and corroborate that with the power consumption, like and energy stats that I'm getting directly from the system. And that's the kind of the second part of it. It's a reader. It really kind of works with the kernel and reads the power data that the kind of like that the application gives me. Then all I have to do is basically tally that and translate that into a power model that basically says like allocates a number of watts to each of these kind of like to each of these processes, and that information is actually what gets put into Prometheus, and you see it displayed in Grafana. In the virtualized use case, it's kind of similar, except that I don't have that information coming directly from from the environment. Like unless the virtualized system runs in my own data center, I don't have that information directly. So I have to kind of make some assumptions in there. If I'm running in the public cloud, for example, I have I have to do like there's even less chance of doing that. So for that, we are using machine learning models that are trained to basically make predictions on the power consumption of an application by knowing how much it would consume, for example, in the bare metal use case. So you can translate that information based on on data that it reads from the virtual machine. In both cases, what I'm getting at the end is a unified and consistent view of my application, like of how much my applications consume, so that I can compare them with each other, right? Now, what do I do? Like, what do I do with this information? As Aric talked earlier, firms need to make decisions. Like, if you're, for example, a drilling company, then your power consumption it's very, very clear what you need to do with it and that you need to reduce it, and it's material. If you're a financial firm, it's more about how your data center works and what an impact you make on your data center. So firms can make an impact there by thinking about their, the way they optimize their infrastructure. As you've seen, infrastructure consumes a lot of power. How do I build better, how do I deploy smaller footprint, operating systems, or, how do I, for example, think about turning off boxes at a specific hours when they are not in use? Or how do I optimize, for example, to put certain jobs at times when power is like less expensive?
Or to shift when you run certain jobs. Think of it the old days, when you had backups. You didn't run all your backups at 6 p.m. You'd stagger them. Okay, So you can do the same thing with your power. If you have jobs that are calculating your capital adequacy, okay, that may take a few hours to run. High power consumption on those, typically. So you can shift when you run things if you have the metrics to understand when things are running. You can conceivably get to the point where you're saying, this transaction, what does it cost me in terms of electricity?
A more radical solution, which is something that certain firms, for example in Europe, are starting looking at, is thinking about moving power-intensive applications to greener data centers. So, I'm kind of thinking, okay, maybe I should put this into, the data center that's nuclear powered, for example, as opposed to coal powered, because that has a, maybe it's not going to make me consume less power, but definitely it's going to make, a lesser impact on the environment. But to me, one of the most interesting ways in which firms can kind of make an impact by thinking about their applications is something you've seen a bit earlier with the two versions of an application, kind of thinking about adopting greener software practices, right? Thinking about like how to use more energy efficient libraries. We kind of think the same way because how many of you are doing application development, for instance, are working in application development? So of course you want to get it's unacceptable to have high latency. It's unacceptable to have low performance. It's unacceptable. So all these are metrics that we kind of think intuitively as participating in this. So this is just one more metric that basically helps you drive, drive your decisions about what you're running. As Aric said, you can run smaller AI models. I don't need to run the 17 billion parameters model when I can run the 2 billion parameter model if I'm not losing precision. But I can get, in terms of cost, they're worlds apart. So it makes it as a gigantic difference. And, kind of thinking in general, as power draw as another design consideration is something that we kind of we're heading into the future. And, if you see, for example, this effort is, something where, if you're familiar, again, with Linux Foundation, the Green Software Foundation is championing. So kind of getting familiar and getting involved with that, I think.
And that last item is something people are doing in the trading space today. They can't deploy certain things they want to deploy, or they need more racks, less densely populated, because of power considerations.
Yeah. So I think in summary, kind of trying to draw it to an end, and this is, I'd be kind of interested if you have any questions or comments in it, is we see sustainability becoming a top concern for firms. It always starts with the more power-intensive firms. They're kind of are thinking first, and they're thinking about power consumption. As I said, if you're if you're an oil and gas company, you will think about power very, very directly. But we see this concern kind of moving into industries that are traditionally, we think of them as less power-intensive, and that's because basically kind of the digital transformation brought us there, and AI is kind of making it even more obvious. And power monitoring is a key tool in the process of actually kind of trying to live in the space. Yes, but that's kind of that's where I was supposed to ask and say what do you think should be there? Fill in the gaps. And again, I think where we want to kind of lead you to is explore Kepler, and think about understand Kepler as a power monitoring tool for your applications, and think about how this type of tool can help you build better, more sustainable applications.
And as you said, it is a young project. So, if you're interested in it, get involved, play with it, feedback, improve it. But there's a ways to go with it. But it's an exciting project that's about a year old, give or take.
It's a bit longer. It's been started by IBM Research a few years ago, and it's been kind of an Intel is a contributor, and
Okay.
Red Hat's Office of Technology has been kind of driving it. But in 2023, it became, so it's a year and a half since it kind of became a sandbox project inside the CNCF. So that's where you can put it a year and a half in public years, so to speak.
Is it interesting to you guys?
Please.
Question in the back.
I'm not trying to be
No.
It's an excellent question. I love it.
No, you're spot on of where it should go. Okay. Kepler at this point is really a monitoring tool because, crawl, walk, run model. You know, but I can see a scenario where you start then looking at it and saying, listen, power costs me X. You know, how can I be more efficient about this? You know, how can I write better code, less vulnerabilities, more efficient, and
So I think
Slow, you might find efficiency in the code to make you faster. You just thought about like how to take the data and pull loop it back to less power.
this is a great.
I
This
think
is
you
a
want to
great
get to that
point.
point. I think you want to say like, hey, I did X number of trades. I'm from a capital markets perspective. I did X number of trades, and this is how much power I consumed. And then, hey, you know, can you do better than that?
This is, I think, where is like there's a lot of room to collaborate with other projects. Like this is more of the domain, I would say, of the Green Software Foundation, like doing that kind of analysis and looking at the code and understanding. You know, where you know kind of where the complementarity is that this kind of gives you a way not to just intuitively figure out that it's actually, but actually measure the application after it's been rebuilt with the recommended practices, and you know provide a justification that yes, we built it and we get the results we expected. And but absolutely, you're absolutely spot on that these two things go hand in hand.
The young man in the front row here has a question.
I found it very interesting, your question. And
I'm happy to see how it goes. I think, have people looking at it.
Yeah, definitely,
Thank you.
definitely look at the Green Software Foundation and what they have, because that's like there's a lot of stuff in there. Any other questions?
Is the data available on like a thread level basis, or is it only like process?
At the pod level.
Okay.
So process pod.
So just that, because we're running on bare metal exclusively, basically.
Right.
So just curious if like we're able to see any
Bare metal on top of Kubernetes bare metal, or just
straight up.
straight
so
up?
So right now Kepler has been, that's an excellent question. Like what you saw is essentially running on Kubernetes and running on, you know, running, and I definitely want to have like hear more about it. There are two other environments where we're kind of like looking at Kepler. Like Kepler originated as a Kubernetes focused project. But right now it's kind of more moving to having support for Linux. So really collecting data at the kind of at the Linux process level. It's still on the individual process, not necessarily at the thread level. Although that would be an interesting discussion on you know on the roadmap. And OpenStack, which was your question wasn't about, but these are kind of like when you kind of have these models and have this understanding of how things work. In the Kubernetes world is definitely expanding into other types of platforms that kind of have you know similar concerns, and Linux is definitely one of them.
Can I ask a broader question? What sort of workloads are you running, and why not run on Kubernetes?
So we're waiting for it.
Sure, because we've done. Again, my background's on the capital market side. We've done a bunch of work showcasing that the performance of low latency applications on top of Kubernetes, specifically OpenShift, is the same as bare metal, RHEL. So if that's, my point is, if that's holding you back, you know, we can have a conversation about, you know, we've got quantitative proof that it's similar.
we do have a customer that's running that low latency
We have multiple customers doing it.
on OpenShift.
A possible kind of like possible evolution of the platform. I think right now the focus was the pod because that's kind of the deployment unit in Kubernetes, but you know there are definitely other ways.
But you got also, I mean, if you've got an HFT app that's just sitting in a loop waiting for, you know, events and stuff like that, there's a ton of other systems around that as well. You know, it's not just you know, a single threaded application. There's a lot else happening there, and you can, you know, improve upon those pieces as well.
So anyway, is anyone coming after us?
I think we should drinks.
Yeah. Okay.
I think we're standing behind.
Well,
In
any
front of these
more
people,
questions?
drinks.
If you have any more questions or comments, or feel free to kind of talk to us afterwards. Definitely interested in any follow-ups. So
And
thanks for being
waitress.
here with us.